Good morning. Welcome to the session of Instrumentation Engineering. Myself, Dr. Somak Karan, Assistant Professor, Department of Applied Electronics and Instrumentation Engineering, Haldia Institute of Technology. And today the discussion topic is control valve problem. So previously we have discussed about the introduction to the control valves. What are the benefits of the control valves? What are the type of control valves are used in different industries? So that already we have discussed. So today we'll discuss about that what are the problems can be occurred into the practical circumstances in an industry because of the control valves. The prerequisite to understand this particular topic is sensor and transducer, control theory, and industrial instrumentation. So before we proceed, we will try to understand that why such kind of problems occur due to the control valves installation or uses. So first of all, we have to be understand the thing very carefully that the control valve is nothing but providing the resistance in a process. So whenever the resistance has been given into a process, so as per the law of continuity, we know that the multiplication of the fluid density, cross-sectional area and velocity must remain constant in the flow stream. That means in the upstream and the downstream side. So whenever the restriction has been provided, which can be considered as an orifice, so in such cases, it is very evidently seen that whenever the area will be reduced, the velocity will be higher. And whenever the area will be higher, the velocity will be lower. That means the pressure is changing according to the change of the area, and the velocity also will be changing according to that. So that's why one of the major point that can be find it out at the time of control valves uses that whenever the fluid will flow through the constructive passageway of a control valve, its average velocity increases. That means we can say that the pressure over there will be decreasing. So as the fluid velocity increases through the constructive passage of a control valve, the fluid kinetic energy or the kinetic energy of the fluid will increase. In accordance to the law of conservation of energy or the potential in the form of a fluid pressure that needs to be decreased. So whenever the velocity will be increased, the fluid pressure needs to be decreased over there. So thus, the fluid pressure decreases within the construction of a control valve stream and it is throttle the flow. Then increase after leaving the constructive passageway of the stream and entering to the wide area. So whenever a fluid is passes through a particular orifice or the control valve, so in such cases, the differentiation or the changing of the pressure and velocity can be occurred in each and every cases because of the restriction or the constructiveness provided by the control valve. So that's why what will happen, the first problem which can be identified, that is called the flashing. That means flashing of a control valve. So if we just try to visualize this particular diagram, we are able to see few of the information over there that if I have a control valve, so obviously the left hand side will be the inlet section and the right hand side will be the outlet section, or that can be considered as an upstream side and that can be considered as a downstream side. So whenever without any restriction, the fluid is coming through a pipeline and come towards the first position of your control valve, which is the upward side of your control valve. So in such cases, obviously here we can see the pressure P1 will be higher. But whenever it has to be passes through the constructive area, so in such cases, suddenly the pressure will drop. And where the less amount of pressure can be identified, this is at the vena contract point. So we have an idea about the vena contract point when we have discussed about the flow using the orifice. So using this particular area of the control valve, so at that particular position, the pressure of that vena contract point will be low because of the maximum velocity. And after that, it is very obvious that the pressure will try to be recovered at the outlet side or the downstream side of the control valve. So the statement of the flashing, if we talk about, if the fluid being throttled by the valve is a liquid and its absolute pressure ever flows below the vapor pressure of the substance, the liquid will start boiling. And it is very obvious that whenever the pressure will fall below the absolute pressure, the absolute pressure will fall below the vapor pressure of the particular liquid which is flowing through the pipeline. So it is very obvious that the liquid will start boiling. And this particular phenomenon, when it happens to a control valve, this is called the flashing. So this is the particular point where we can see that the pressure is minimum and the velocity is maximum. So whenever if this PVC is less than the vapor pressure of the liquid which is flowing through the pipeline, so in such cases the liquid will start boiling, and this particular phenomenon will be considered to be as a problem which is identified as a flashing. So from the graph itself, the point of the lowest pressure inside the valve, which is nothing but the vena contract pressure, PVC, is the location where the flashing first occurs. So it is very important that the flashing will first occur at the point where the velocity is maximum and the pressure is minimum. And if the PVC, that means the pressure at the particular vena contract point, is less than the vapor pressure of the liquid which is flowing through the pipeline, then obviously the problem which is named as flashing, that will occur. So now if we just go to the next discussion, what are the effect of flashing if we try to understand? So obviously if such condition will happen and your liquid starts boiling, it is unacceptable. So the flashing is almost universally undesirable in a control valve. So the effect of boiling liquid at the point of maximum construction is that the flow through the valve becomes choked. So obviously when the particular liquid will start boiling, so it will take maximum areas of the maximum space. So it will stop the flow of the liquid and choke. And obviously the rapid expansion of the liquid to vapor will make it boils. So it is very obvious that the total flow rate allowed through the valve will be restricted. Flashing is also destructive to the valve trim because here a huge generation of the boiling of the liquids will happen. So obviously the flashing is also destructive to the valve trim which is connecting the particular plug to the system. As the boiling action propels the tiny droplets of the liquid at an extreme high velocity past the plug and the sheet face, eroding the metal over time. So whenever this particular boiling will start, and accordingly rapid expansion of the liquid to bubbles will come into the picture. So in that particular time, obviously it will try to take the higher velocity and obviously give the destructive approach towards the trim and the plug. So there is one of the diagram through which the particular eroded valve plug and the body can be identified. So here we are able to see that how much destructive is the flashing is. So from the photograph itself is showing the practical output that when the flashing has been occurred into a control valve, so how the eroded valve plug will be coming out after the particular flashing has been occurred for maximum amount of time for a particular duration. So now if we talk about the next point which is known as cavitation. So one of the very interesting point has been noted down for the control valve problem, that flashing is the cause and cavitation is the effect. That means if the flashing has been occurred due to the pressure drop at the vena contract point of the liquid lower than the vapor pressure of it. So in such cases, if the particular flashing has been occurred, so there will be no chance that the cavitation will not be occurred. So cavitation will obviously be occurred because of the occurrence of your flashing. So that's why this statement is very important, that flashing is the cause and cavitation is the effect. So now we'll try to understand that what is another type of issue or the problem we can say can come out for the uses of control valve, and if the flashing has been already happened, how the cavitation will come into the picture. So if the fluid being throttled is a liquid and the pressure at the vena contract is less than the vapor pressure of that liquid at the flowing temperature, yes, one of the very important point is temperature is very important, because as per the law of continuity, there is the density multiplied with the area and the velocity. So if the temperature will change, obviously the density of the liquid also being changed. So the temperature needs to be constant at that particular point, and the liquid will spontaneously boil, which is already known things to us. We have discussed about it, and this is the phenomenon of the flashing which previously we have described. Now, however, the pressure recovers to a point greater than the vapor pressure. It is being very obvious that whenever the liquid will come out from the narrow passageway of the control valve, the area will be larger. So whenever the area will be larger, so obviously your pressure will be higher, your velocity will be lower. So whenever your pressure will be higher than the vapor pressure of that liquid, so again the bubbles will try to recondense, and whenever the recondensing has been happened, so in such cases the liquid will again make their own area. So that is the point, that if however the pressure recovers to a point greater than the vapor pressure of the liquid, the vapor will recondense back into the liquid again, and this particular taking back the particular vapor to recondense to the liquid is known as cavitation. So that's why I am telling that the cavitation is the effect, flashing is the cause. So whenever the flashing has been occurred, in such cases only the thing will happen that your particular liquid starts boiling. And if the particular liquid starts boiling, in such cases, there will be the condition of recondense back of the vapor to the liquid, and this particular recondense back to the vapor from the liquid from the vapor is nothing but called as a cavitation. So how the cavitation can be identified? So from this particular diagram, the things can be understood very clearly. So here also we have the control valves upstream side. This is the upstream side, and this is the downstream side. So we can say up and down. So liquid will come through the pipeline and it approaches towards the upstream side of the control valve. And obviously the P1 pressure, we can obviously say it is higher than the vapor pressure of the liquid which is flowing through the pipeline. Whenever it will try to passes through the narrow constructive area of the control valve, so here we can see it is suddenly reduce the pressure and increase the velocity because of the reduction of the area. So whenever it will go down to the particular vapor pressure of the liquid, so this is the point we are able to identify where the first flashing has been occurred. So whenever the first flashing has been occurred, so in that particular point we can say the liquid starts boiling, and it will try to hit to the trim and the plug of the control valve, which is very destructive. And after that, whenever it will try to passes through the control valve area, and one time will happen that whenever the area will be larger, so obviously the pressure will be higher and it will try to go up of the vapor pressure of the liquid. So whenever the vapor pressure of the, that means the pressure of the liquid will move up to the vapor pressure of that particular liquid. So here the vapor will try to recondense and back to the liquid. So this is the point, here we can say this is the point of the cavitation where the cavitation occurs. So these are the, from this particular diagram, these things can be very easily understood, and this both condition of the flashing and the cavitation is very dangerous. They both are harm the entire body of the control valve, the plug of the control valve, and we are trying to be define the system or try to be recondensed the particular liquid before it happens to the flashing or the cavitation. That is the most important part of the discussion. That means how the problem of the control valve can be eliminated. So now we have some of the points which we have to be discussed, because we have already discussed about two of the problems, which is the control valve problems considered to be as a flashing and cavitation. So as destructive as flashing is to a control valve, cavitation is the worst. So as I already mentioned that the flashing is the cause and the cavitation is the effect. So if the flashing can be called as a destructive, the cavitation is the worst condition happened into the control valve. When vapor bubbles recondensed into the liquid, they often do asymmetrically. Obviously, when the vapor bubbles will recondense into the liquid, so it will not do the symmetrical action. It will asymmetrically recondense at the particular area of the cavitation, and one side of the bubble collapsing before the rest of the bubbles. So this has the effect of translating the kinetic energy of the bubble collapsing into a high speed jet which is attacking, or which is try to be hit to the control valve's body. That can be the plug, that can be the trim, which is nothing but hamper the entire system. What is more, that the pressure applied to the surface of the control valve components in the path of this microjet is immense. That means when this microjet will try to be hit to the particular body of the control valve, it damages the most. So that's why we have talked about that if we are talking about flashing is destructive, that means the cavitation or the effect of the cavitation is can be considered as a force. So each microjet strikes the valve's component surface over a very small area. So because the orifice is a very small area, or the small area of the valve to which the liquid can be controlled. So that's why, because in a very small area, the strikes of the microjet will hit repeatedly if the flashing and the cavitation has been happened. So it will make an immense effect into the valve plug and the body, which diagram already I showed to you. No substance known is able to continuously withstand this form of abuse. That means no metals can be take this particular amount of strikes each and every time as a form of a microjet by the vapors when it will be recondensed into the liquid. The effect of each microjet implying on a metal surface is the curve of a small pocket in the metal surface. So whenever this particular microjets will hit into the valve body, mainly the valve plug and the valve trim. So in such cases, there will be a pock mark look over the area of the cavitation. So it is very, very dangerous over there. So it is very important to identify that why such condition of the flashing has and the cavitation has been occurred. So it is very obviously understood by us that whenever the liquid which is flowing through a pipeline of a pipeline and try to passes through the control valve. So in such cases, if the liquid pressure will ever fall below the vapor pressure of the liquid in a control valve, mainly towards the area of the vena contract point. So in such cases, flashing obviously will occur. And if the flashing will occur, there will be a no chance that you can restrict the cavitation, because the cavitation have to be occurred if the flashing has been occurred. So in such cases, what the remedies, what are the elimination process we can be applied, that we will discuss into the next part of the discussion, which is the uh, elimination or try to be reduction of this particular type of problem of flashing and cavitation from a control valve. Thank you. We'll meet in the next part of the lecture of the control valve problems. Thank you.